All right, good morning, enthusiasts for quantum computing. This is the last lecture, and it's basically going to be a recap lecture. We kind of did it all in terms of quantum algorithms for classical problems. We hit the highlights, and this is a traditional place to end after we've done like factoring and Grover's algorithm for SAT. So we're just going to recap a little bit about what we saw throughout the course and try to reflect on it. And yeah, I put quantum algorithms here because actually, maybe the title of the course has quantum computing in it, but really, I suppose, ultimately, it was about quantum algorithms that we studied per se. So that's what I want to recap today. Okay, so let's try to look at like what happened and like how it happened and why it happened. So we might go all the way back to lecture. I'm just going to recap some highlights. So back in lecture 7, one thing we studied there is that, basically we saw that quantum computers are at least as powerful as classical computers. I mean, even if you don't mix in classical computing, anything you can do with bits, you can also do with qubits. So we saw that, like, given some classical code operating on, data type bits, you can make equivalent quantum code that does the same thing on qubits. And equivalently efficiently. Okay, now you have to be a little bit careful because, of course, any quantum code is ultimately going to be represented by like a unitary transformation, and therefore it has to have the property of reversibility. But with some suitable like convention of what it means to compute a function, that it's not itself reversible, like this if f then minus or if then toggles, you can make it happen. Now, you wouldn't do this just for fun. Like if you had some classical code that was working well, there's no reason to like do it all over again with qubits, unless the whole point was you're going to use the quantum feature of doing this computation in superposition. So the real reason you would want to do this is then instead of putting in like, one input string and running the code and getting the results, as you could have already done, you can put in a superposition of input strings and get out a superposition of input-output pairs. So this we saw in lecture 8. We saw that it's like easy to produce the uniform superposition over all, let's say, 2 to the n many n-bit inputs or n-bit strings. And then, if you have some classical code that does a computation on n-bit strings, you can do the same thing with the quantum code and thereby get the superposition over all, let's say, 2 to the n input-output pairs. Okay, and one theme I kind of want to think about a little bit in this lecture is like, where is the real power of quantum computing over classical computing coming from? And this seemed like an obvious place, like, this computing in superposition, like computing all the answers simultaneously. And I do think that is true, and that really is one of the crucial components of quantum computing. It may seem obvious, like obviously this is the truth, but it's not so obvious actually when you think about it a little bit at first, because you can do a very similar thing with classical probabilistic computing. You can take some classical code that operates on bits, and you can pick a uniformly random input from among all the 2 to the n possible inputs, and then you can have your computer compute the output for that input. And maybe if you don't look at the results yet, you could say, all right, well, the situation with my randomized code is it's like the uniform probability distribution over all possible input-output pairs. So it doesn't look so different from this, per se. And indeed, we saw that like when you get to this situation, if the next step of your algorithm, your quantum algorithm, is to just measure all the qubits, then what you will see is a uniformly random input-output pair. And we know that's nothing special. You could have had that all along with just randomized algorithms. So this cannot be the only aspect of quantum computing. And in fact, so far, it seems like we don't get any extra power. So then we might have to think about, like, OK, well, how did we get any mojo out of this? And it seemed to come from the fact that this uniform superposition over all 2 to the n input-output pairs, it's got amplitudes rather than probabilities. And amplitudes can be negative besides being positive. And subsequent manipulations can, thereby add and subtract the possibilities in some vague sense. And seemingly, sometimes you can arrange the subsequent computations to, like, add together the, input-output pairs that you want and, like, cancel out the input-output pairs that you don't want, or something like that. So one such manipulation that we studied in quite some detail in lectures maybe 6 through 9 was this Hadamard transform, which was just doing the Hadamard operation on all your qubits. And I even called it like a paradigm because to the extent that there is any unifying algorithmic theme in like all 4 or 5 algorithms we saw over the course of the course, maybe this is one of them, like doing a Hadamard transform or some kind of Fourier transform. So just to remind you about this, this paradigm was you're given like, classical code, let's say, computing a function with like n-bit inputs and let's say 1-bit output. What did you do? Well, you did this process. You like prep the uniform superposition over all input strings. And then you kind of compute f on all the input strings. But we use this convention for computing 1-bit functions with 1-bit output, where you could kind of compute it in the signs. We showed that you could cook up this like if f then minus instruction. And that got some negative signs into the picture, which seems maybe helpful if you're going to use this this power of quantum computing. And so once you did that, like now, the 2 to the n amplitudes are like the plus or minus truth table of f, you might say, if you remember. And then you do the subsequent, manipulations that perhaps make some things cancel and some things positively interfere. So we saw that you do this Hadamard all. Okay, and then maybe you measure or extract at the end. And this gave you some weird information about f. And we actually took some time to understand, like, what is this? This is like maybe the only algorithm we could think of doing. So it's instead of trying to think about what we want and like design an algorithm for it, we like thought of an algorithm and just saw what we could make of it. So one thing we saw is that, I'll write over here, resulting amplitude on the all zeros string, that had some nice meaning. It was the bias of f. So basically, if f's truth table was like all ones, this would be, I guess, -1. And if f's truth table was all zeros, this would be +1. And if f's truth table is 50-50, this would be 0. And in general, it would measure how biased the truth table was. And that's kind of interesting. And then more generally, we worked a little bit to show a meaning for all the other amplitudes. The amplitude on a bit string B1, B2, up to Bn was the correlation between f's truth table and the truth table of this bit-masked XOR function. okay, where if this is a Boolean string, you kind of like apply it as a bit mask to the input, and then you XOR together all the resulting bits, and that's some other Boolean function, and this amplitude measured how similar this kind of input function was to that XOR function. And to use a little fancy math jargon, like these numbers are, all these 2 to the n numbers are sometimes called the Fourier coefficients of f for a Boolean function. And so the resulting amplitudes after this whole process give you these Fourier coefficients, these 2 to the n numerical bits of information about the function f. And then if you measure, you'll kind of see a bit string with probability proportional to the square of this correlation. So you'll kind of get like a signal about like which bit-masked XOR functions have the most correlation or the most anti-correlation with f. And again, that's kind of a funny thing. Again, it's not like we set out to solve a problem and designed an algorithm. It's like we took this weird algorithm and it gives us this odd information about f. Now, this is like a process that we wouldn't know how to do with a classical computer. So in some sense, then, people in the olden days of the early 90s maybe racked their brains to think a little bit like, what could you do with this information? And I guess they came up with some somewhat interesting things you could do with this algorithm that maybe had the property that, we don't know how to do these things with a classical algorithm. And yeah, let's take a look at them again and maybe try to judge them on a few axes, like are they solving an important problem? Are they getting a really great speed up over classical computing? Are they practically interesting? Are they theoretically interesting? We're going to reflect on these algorithms we've seen. Let's get this going. I can start here. Yeah, so one thing we did, this is kind of like Hadamard transform use number 1. Was this bias busting algorithm, as I called it. If you go out into the wider world, you'll hear them call it the Deutsch-Jozsa algorithm, after the 2 people who came up with it. And so as a problem, bias busting is just trying to tell if the bias of the function computed by your code is non-zero or 0. And the way the algorithm works, which is to just do this process and measure and then see if you get all zeros or not. And if you do get all zeros, you can output that it's biased. So given the code for f, it outputs either biased, or it outputs no comment. And it's an efficient algorithm and has like a couple of properties. It has like no false positives, so it never outputs biased when the function actually is unbiased, has bias 0. And it has like some quote unquote positive power, which is to say that if f's truth table really is biased, then the probability that it outputs, biased is positive. Okay, so that's one thing you can do with a quantum computer. And now, as I said, we want to think a little bit about, is this good? What do we think about this? I mean, one nice thing about this algorithm, I kind of like it, is it does sort of demonstrate, I guess there's a clear link between the algorithm and these 2 principles that seem to be the power of quantum computing, like computing in superposition and making interference where positive and negatives cancel, I guess. So one thing we can ask is, okay, for bias busting, is this an important problem? And at first you might think, like, I don't know, I never heard of this before. Like, given some code, try to tell if it's computing a Boolean function which is biased or unbiased. And that's true. But actually, if you did some homework problem, I think it was 4.6, we saw that actually the SAT problem reduces to bias busting, which is to say that if you had an efficient algorithm that solved bias busting 100% of the time, or solved it with high probability, then you would get an efficient algorithm for solving SAT 100% of the time, or with high probability. And SAT is like the most famous and most important, outstanding difficult problem in computer science, and therefore that kind of makes bias busting in some sense a very important problem, because if you could solve it efficiently and effectively, then you'd also solve SAT. So that would be great. Okay. Now, another thing I want to look at for all the algorithms we studied is like, is it actually giving us like a really major speed up of our classical algorithms? And for this problem, I guess in some sense the answer is no. Because while it's true that if a classical algorithm is going to solve bias busting, like really tell the difference between biased and unbiased, like effectively with high probability, it will take exponential time. This algorithm would also take exponential time if you really wanted to solve it. And as you remember, that's because this greater than 0 is working extremely hard here in the sense that this positive probability might be exponentially small. So if you really wanted to get like a confident sense of whether your code is computing a biased function or not, if you just run this, it's probably going to say no comment. You run it again, it'll probably going to say no comment, and you have to run it like exponentially many times to be sort of really sure that it was not biased. So in that sense, it's not really giving us any major speed up over classical computing. But even though it's not practically interesting, I'm a theoretical computer scientist, so this is like theoretically interesting. For the following reason, as we mentioned when we talked about it, this is a very peculiar and not practically helpful way to, solve or try to solve the bias busting problem. However, suppose for whatever reason you were like, this is what I want. I just want an algorithm that has absolutely no false positives and some positive power. It's useless, but you could say that's what you really want. Then we're extremely sure there's no classical algorithm with these properties. So this was proven, before quantum computation was pretty much even a thing by Ogihara, maybe also Toda in 1990. They're just studying computational complexity, and they showed that assuming something extremely similar to p does not equal np, so I'll write p does not equal np, but it's actually this complexity theory thing, but something very similar to p does not equal np. No classical algorithm can have this same useless behavior. So what's nice about this is, so it's theoretically interesting because it kind of tells you that you should not expect somebody to wake up tomorrow and show that there's a classical algorithm that can efficiently simulate quantum algorithms. Because if there's a classical algorithm that can efficiently simulate quantum algorithms, you would get a classical algorithm with this behavior, and we kind of know that's impossible. Okay, so that's some confidence boost that maybe there's something to this quantum computing. So then I'll remind you of our second use of this Hadamard transform principle. And we saw it way back in even lecture 1. Paradigm use 2. And that was mystery toggles, if you remember. We saw it in lecture 1. We eventually wrapped it up in lecture 9. There's this mystery toggles problem/algorithm. And this was originally done by Bernstein and Vazirani. So if you go out into the wide world, nobody will say mystery toggles. They'll say Bernstein-Vazirani algorithm or Bernstein-Vazirani problem. And this problem was like pretty much literally exactly cooked up by virtue of this algorithm. It's like, well, this is the algorithm we have. Let's literally define like the problem that it's basically solving. Oh, thank you. So, the task is, you're given code for f computing some bit-masked XOR function. So somehow you know that this code you have computes a bit-masked XOR function. Not sure how you get into this scenario. But you don't know what the bitmask is, and your task is to learn the bitmask. So given this, a quantum algorithm can learn the bitmask, B1 through Bn, with just like one call to the code. You make the uniform superposition. You do if f then minus, and then the result is that like literally 100% of the amplitude, like one amplitude, is on the basic state corresponding to the actual bit mask by virtue of this fact, and then you measure, and then you see that bit mask with 100% probability. And cool, so that was fun, and it made for a nice demonstration in our first lecture of quantum computing doing something cool. So let's again think about like, okay, how do we feel about this as like an amazing demonstration of quantum computing? And it's got some pluses and minuses. So is this an important, task? Well, no, I guess not, right? I mean, it's like literally an invented problem. And it does have the flavor of like a learning problem, but it's like hard to conceive of a scenario where like you have some code that somehow you magically know is computing an XOR function, even though you don't know what that XOR function is. Okay. Is it a major speed up over classical algorithms? Well, I think the answer to this one is like yes and no. So why do I say yes and no? For the same task, I mean, we basically saw, or maybe even proved in the homework, a classical algorithm would have to make like n many calls to the mystery code to figure out the bit mask. Because basically, when you call the code, you get back one bit of information, and you're trying to learn n bits of information. So you need to make n calls. So you might say this is like a truly amazing speed up because 1 is like literally 1 for every value of n. Like n could be 10, n could be 100, n could be 1,000, n could be 1,000,000. And like you're always solving with like 1 unit of work here, and you're solving it with n units of work here. Sometimes it seems like it's even better than exponential. But that's not quite right, at least from a practical point of view, because although the quantum algorithm only has to make one call to the code, it does do order n work, or it has order n many instructions in the actual code. Because among other things, it has to make the uniform superposition, and that's like n Hadamard instructions right there. So in fact, maybe if the code itself, running the code takes time t for some parameter t. In fact, really, the amount of time or work the quantum algorithm does is order n plus t, because it does order n Hadamards, and it runs the code one time. Whereas this classical algorithm that calls the code n times, it does like order n times t work or time. And now, this is still better than this, but it's not like arbitrarily, it's not like way better. In particular, like you can just, I'll actually mention, this is like a square root speed up for quantum. Why do I say that? Well, it depends how t compares to n. If t is way smaller than n, then this is basically n, and this is basically n. So they're about the same. If t is way bigger than n, then this is basically t, and this is basically t. So they're about the same. So like the hardest case is when t is roughly comparable to n. If t is roughly comparable to n, then this is about n, and this is about n squared. So even in like the worst case, or the most favorable case for the quantum algorithm, when t is sort of proportional to n, this is like n squared, and this is n. So that's nice. We got to speed up from quadratic to linear. But okay, it's not like an exponential speed up like we might have had in our hopes and dreams. Okay, we might finally ask about, is this theoretically interesting? And it is theoretically interesting because it does show like a very wide gap between, like in this model where you only count the number of calls to the mystery code, this is sometimes called the query model. You'll hear that a lot if you read about quantum computing, the query model, where you don't count time per se, just number of times you run some mystery code. This is a big separation. It's like 1 for quantum, and it's n for classical algorithms. There's one more application of the Hadamard transform paradigm that we didn't talk about in this class, but it's often taught in other classes. This is called Simon's algorithm, or Simon's problem. Just write the name here. And again, this is like a problem cooked up by this postdoc in Montreal, Dan Simon, who was taking this paradigm and trying to squeeze like the absolute most juice out of it. He's like, what problem can I design that this algorithm will be like best at like solving? And he designed another one. It's not too complicated. And got a similar situation where with quantum, it's another one of these things where you get like mystery code that you're magically promised computes a weird type of function, and you're trying to figure out what type is the function. He showed that quantum can do it with, n calls to the mystery code, but like classical, you need basically 2 to the n calls. And this is really better. I mean, this is like an exponential gap. And even if you factor in like the running time for the code, t, it would show an exponential improvement for quantum algorithms. So it was an algorithm for a very strange and not important problem, but it maybe also gave a vivid demonstration that quantum algorithms can do something exponentially better than classical algorithms. And maybe I mentioned back when we talked about it, Simon's algorithm like directly inspired Shor's algorithm for factoring. So Shor's algorithm for factoring, which we didn't do, we did a different algorithm for factoring, uses the Fourier transform, a Fourier transform as its central subroutine. Okay, so that was sort of the first half of the course. And in this first half of the course, I guess it was a lot about this idea of computing in superposition and, getting amplitudes that are positive and negative and making them interfere and cancel out in nice ways. So, I don't know, so far, if you ask me, like, what is the real reason quantum is more powerful, I would still be like, I'm not really sure, but I guess it's this interference and computing in superposition. But it's funny because we really only saw, like, with these ideas, we kind of came up with one algorithmic idea, and we were like, well, if this buys you something, great. Otherwise, we didn't have too many subsequent ideas.